Yo, what's up, everyone? So, this is the last probability question, and in my opinion, this is like the best question of the whole set because it's going to talk about all three big kinds of probability: binomial and normal, like we've been doing, but then also sampling distribution, and that's going to be a whole set in itself. But this is going to be like kind of like a little bit of a teaser to that. And that set is going to be pretty small. So this is like one of our big opportunities to learn about the sampling distribution. And the reason I like this question, we're doing number 6 here, but I think it's going to be number 4 in your packet, is it's a pretty short question. But each part of this is a different type of probability. And for this AP exam, I've been looking at the teacher community, the AP statistics community, and this is unlike any other test, and people don't really know what's going to happen. But if there's only going to be 2 questions, and it's open note, it seems really likely that they're going to try to throw a bunch of different things into that question. Okay, there's no way that it just asks you to describe a histogram, create a box plot, and keeps it into like a singular unit. It's much more likely that this question is going to span multiple different things. Okay, so this is kind of a good example of what the AP could do for like the probability question. But I think it'd be even longer than this, honestly. But let's talk about what's given and how we could determine what kind of probability question we're doing. It's talking about tire manufacturing. Read the question, I'm going to read it too, and then I'll give you the gist. Okay, yeah, this is like the most basic. This is actually, I like this a lot because it's giving us, and I like this question a lot because this kind of looks more like something I would give you. It's really, really simple. It's just talking about how long these new tires last, and it tells us the mean, the standard deviation, and that it's approximately normal. Okay, so we'll say mean equals 125 and standard deviation is 6.5. And I love this because it's cool how many different things you can do given so little information. So the first thing it says is what is the 70th percentile of the distribution? And that's wording that we haven't seen in this set yet, and this is the only time I saw it in one of these, but we did it back in the day. If you see percentile, that just means like percent below a point. Okay, so if it says the 70th percentile, just remember that means that you're better than 70% of people. So that means that this area under this point is 70%. And it's saying what is the 70th percentile? So we want to figure out for the tires, 70% of tires do worse than this distance. Does that make sense? And we did similar questions before. What only could be hard is maybe this percentile. We're going to approach this the graph and calculator method. That's what I'm going to do for this entire set. Because some of you might feel better about fooling around on the graph and calculator. You never use NPD. Like, you never use NPD. Let me put that in the notes so you write that down too. Like literally never, because it doesn't even make sense for a continuous variable. But if we're going to do inverse norm, tail, area. Oh, I was so confused. I did this question on my own before. That's why all the right stuff is in here. But inverse norm, you can take a percent and you can solve the entire thing. Like, the other way that we tried to do this is find the z-score first. But if you put this in the graph and calculator, it actually does it for you without finding the z-score. Again, you could find this in the chart, plug it into the z-score formula, etc., etc. But if you know your inputs, the calculator is going to crush it for you. So here, the tail is the left side, because that's the shaded region. The area is 0.7, and then our 2 Greek letters, which I've gotten pretty good at drawing, not going to lie. But this one that kind of looks like an M is mean, and it's mu. And then this one that looks like a yo-yo. Do you see what I mean? it looks like a B that fell over. No, like more like a P that fell over, or a 9 that fell over. Like it's like a baby whose head is too big. It can't like hold itself up. So it was like, that wasn't even funny. So I probably should actually delete this one. But what I don't like about this, what I'll say, is that it puts standard deviation before mean. And some of these, when I was reviewing again, I mixed that up. And if you flip the numbers, it could be deceptive in that it still seems like it's the right answer. Like an answer, like it says 72, and that seems like a number that makes kind of sense, right? Just make sure you're putting them in the right place. And it really doesn't make sense, because if the center was 125, this point has to be greater than that. So we can say data point equals 128.41. So that's normal distribution, okay? And if it says anything like percentile or that kind of thing, that's going to be normal distribution. But your clue always for the second one. So the second one says, what is the probability that at least 2 cars out of 5 randomly selected in the study will stop at a distance greater than calculated in part A? Okay? And your clue that this is binomial distribution is phrasing like 2 out of 5. Okay? So when we do binomial distribution, we're trying to find the probability of this event and then the X and the number of trials, which are going to be related to this 2 and this 5. But this question, I think, is deceptively tricky. So let's talk about exactly what it's saying. It says, what is the probability that at least 2 out of the 5 cars randomly selected in a study will stop at a distance greater than the distance calculated in part A? So the distance calculated in part A, and like this is going to be, I want to talk about how you can do tests, because students I know get really intimidated on tests and really like to shut down, but you have to just go one step at a time. Okay, so if it says will stop in a distance that is greater than the distance calculated in part A, what was the distance calculated in part A? That was 128.4. Okay, so we want to figure out the percent that stopped greater than this. Okay, and all you need to think is it already told us that 0.7 was the percent of data below that point. So what is this percent? That'll be the opposite, or 30%. So in part A, the distance calculated was 128, and 30% of cars are at a distance higher than that. So when we solve this, P is going to be equal to 0.3. And when you're doing this, there's only 3 things you need. And I mean, in this case, you will do 1 minus one of them, or like the whole thing. But P could be the hardest thing. Next, we have X and number of trials. And this is where I'm going to draw what's happening. The binomial distribution is discrete, meaning you can't be in between any of these options, right? So think that like 2.3 cars can't be greater than this distance. You either are or you aren't. So if this question is saying at least 2 out of the cars in the study are going to be greater than this percent, that means 2, 3, 4, and 5. And remember that for the normal distribution, you can only find data below a point. So if we plug in 1 for X and 5 for number of trials, that's going to give us this percentage. And once we have this percentage, we do 1 minus that, and that gives us this percent. So in my opinion, this is like one of the hardest parts of the whole year, because for stuff like normal distribution, you don't have to do 1 minus when you're finding the opposite, but this is a unique binomial distribution issue. If it said less than, you would have just done 1 and 0, right? But because it's at least, this is what we're going to do. But that is it. It's going to be easy now. So it's going to be 1 minus 0.528. Okay, so with that, we're completely done. with our normal distribution and binomial distribution review. And now we're going to talk about the sampling distribution, which is conceptually very hard, but not the hardest thing to solve. And this is going to be like a thorough kind of explanation of it, because I haven't decided exactly what questions I want to do in the future. And if I can explain it now, might as well just do that. So it says, what is the probability that a randomly selected sample of 5 cars in the study will have a mean stopping distance of at least 130 feet? Now here's the big concept. This graph represents what's going to happen to a single car, right? Okay, so what makes this difficult and interesting is that we're no longer talking about what's going to happen to a single car, okay? We made that graph before, and we know that we can find probabilities about this many cars will stop at this distance, that we can find percentiles. But the end of the year is all about what happens when you take a sample and how likely different outcomes from your sample are. Because if we know what happens in a random sample, we can use that to predict the truth. But all of that only works if we can create some kind of distribution that represents how likely certain sample outcomes are. Okay, so we're talking about the sample of 5 cars. How likely is it that that sample of cars is at least 130? But it's not as simple as just doing 130 divided by 125. So 130 minus 125 divided by the standard deviation given to us. Okay, what we have to do first is find the standard deviation of the sampling distribution. We know that the center of the sampling distribution, we know that if 125 is the truth, as it told us in the beginning of the question, that's going to be what happens the most frequently, okay? Most samples are going to be really close to 125, and think that the larger the sample, the more accurate it is, and the closer all of them are going to be to the center, okay? Hopefully we remember that concept. But all we do is find a new standard deviation. So if you're just given a normal distribution question, you're going to use the standard deviation that's given to you. But if it's talking about a sample, you have to now find a new standard deviation. And one hint that always really works for me is we know that the number in the sample affects the standard deviation. A really big standard deviation means that all the samples are going to be really accurate. But a really small one like this means that the samples could be really varied. It's possible you get 5 cars that are all duds or 5 cars that are all studs. Haha. So we have to take the standard deviation given to us, 6.5, and divide by the square root of sample size. There's 4 formulas for this depending on what we're doing. This is a mean question, and there's only one sample going on, so this is the formula. So you can see that if you were given this question on the AP, they're asking you a lot of different things. But none of them in this question are too bad. So that would be the standard deviation. That gives us context, and we can already predict the z-score is going to be like 1.7 or something like that, because this and this are 5 apart, this is 2.9. Does that make sense to everyone? So for a single car, this is the distribution with this standard deviation. But if we're taking samples of 5 cars, this is the standard deviation for how much they vary. And once you have your standard deviation, mean, and data point, you can plug it into the calculator, and I'm going to use that approach this time. With lower and upper, we're trying to find 130 or greater, so 130 to infinity, with a standard deviation of 2.9, and the same this. I got that standard deviation really close. I mean that z-score really close to my head. Shut up, Johnny. Okay, so that is the value. And it's not a p-value yet because we're not doing any kind of test, but that is the gist of that question. And we'll do more sampling distribution in the future. But again, if you see a sample size, you're going to have to use that sample size in your equation. But yeah, I think that went really well. And after this, if you've watched this video, you're over halfway done with the whole thing. and the second half is stuff that we've done more recently. So this is kind of, in my opinion, maybe the last super important video to watch, because the rest of it is more review. You might be able to get away with the inference stuff without even watching. So if you're with me, you're in good shape, and I'll see you next time.
Woo!